All right. Yeah. Thanks. Thanks for the invitation. Thanks for coming, and welcome to all of you in the room and on the screen. Yeah. So today's talk is to some extent a continuation of yesterday's talk, but it's, I hope, sufficiently self-contained that you can also listen to it if you didn't listen to my talk yesterday. So the application of the trace formula that I have in mind has to do with so-called density theorems. And let me briefly recall or just give the setup. I take a finite family of, let's say, cusp forms to keep things simple, or let's say automorphic forms on GLN over Q, finite but large. I take a fixed unramified place Q, and I want to check how many elements in F violate the Ramanujan conjecture at V by a certain degree. And I measure this as follows. At V, every element comes with a set of n length parameters. If I have trivial central character, then they add up to 0, so I have n-1 degrees of freedom. In any case, for my given F at V, I have n length parameters where I runs from 1 to n. And on Ramanujan, they would all be purely imaginary. So I look at the real part of those, take the absolute value, and take the worst guy. Yeah, the value of I where this becomes maximal. And this is what I call sigma F of V. If this is 0, then my F is tempered at V. And if it's bigger than 0, then something went wrong, perhaps. And I want to count how many elements in F have a value of sigma F of V that's bigger than some given sigma. That's why what I denote by NV of sigma F, that's the number of F in F, such that sigma F of V is then sigma. And the idea is the bigger sigma becomes, the smaller this set should be. Yeah? So somehow the more Ramanujan is violated, the fewer enemies I'm supposed to have. And we have the following trivial bounds. Well, trivially, this is bounded just by the size of the family. There's nothing deep about that. And the worst form that I could look at is the constant function or the trivial representation at any place V is sitting at n-1 over 2. So that's the extreme case, that's the extreme violation to Ramanujan, and the goal is I want to linearly interpolate between these two bounds. So what I want to show is that this is bounded by the size of the family, which is the trivial bound, 1 minus a constant times sigma plus epsilon, and the constant that I would like to have is 2 over n-1. Because this is the right constant. If sigma is n-1 over 2, then I just get exponent 0. So I get just a constant, like a constant number of terms. And if sigma is 0, then I get its law back. Yeah? So this is somehow the correct value of C in some sense. Okay, the families that we are looking at today, our families will always be families in the level aspect. I don't know how to treat families in the eigenvalue in this aspect, so the Archimedean aspect. I'm treating families where the level grows and the Archimedean component is fixed. So we have level families for congruent subgroups. Okay, with fixed Archimedean component. So if the Archimedean component is fixed, then it's in particular a finite number, but the smaller my congruent subgroup becomes, the larger the family becomes. And there's another small simplification. This is more for expository purposes. I assume that V is a finite place. The infinite place is pretty similar, but that's for notational simplicity. Let's assume that the place is finite. Okay, so this is what I want to talk about. This is the application of the trace formula. I want to apply the relative trace formula to get a bound like this, which is called a density theorem. I talked yesterday about possible applications of such a density result, and it's certainly something useful to have if you can quantify how much Ramanujan is violated depending on the degree of violation. Okay, and we want to see the trace formula in action today, and I want to show you what input you need in order to actually apply the trace formula. Okay, so what's the starting point? Okay, we want to bound this quantity, so let's write down what it is. It's by definition the number of all f such that sigma f of v is bigger than sigma. And as I said yesterday, we use a very simple trick. I mean, this summation condition is a bit inconvenient, so we attach a weight that's bigger than 1 if this condition is met. And I do this by writing p to the 2 sigma f of v times m divided by 2 sigma m. Well, obviously, if sigma f of v is bigger than sigma, then this weight is bigger than 1. And I can m choose in any way I want, and p is my p. All right, so m is a free parameter. Okay, and it's not very hard to see that, okay, if Ramanujan is violated, then somehow I can detect this by looking at Hecke eigenvalues of large enough prime power. This is related to the asymptotic behavior of the p-adic Whittaker function at 0. So this is roughly, I can take out the denominator, and this is roughly p to the mth Hecke eigenvalue squared. Yeah, I have 2m, and this is also 2m up to some Hecke relations. This is roughly what we need to do. Okay, and I want to apply the trace formula to this, but not really the trace formula, but rather the Kuznetsov formula. The title is Applications of the Relative Trace Formula. And so for the relative, so now somehow the trouble starts. In order to apply the relative trace formula, I need Fourier coefficients and not Hecke eigenvalues. And so let me sneak in a first Fourier coefficient. We'll see later whether this is allowed or not. So let's hope that what I'm going to do is allowed. And I will talk about this later. So let's just sneak in a first Fourier coefficient. Okay. Let's pretend I can do this without too much loss. And now we are in shape to apply the Kuznetsov formula. And the Kuznetsov formula has the following shape. I'm not tall enough, but maybe okay. So what you get is the following. You still have the denominator. You get the volume of the subgroup. So let me call this volume. This is somehow the co-volume of the subgroup you're looking at. And then it's parameterized by Weil elements in the Weil group. And then you get Kloosterman sums. So you get moduli C. They are in fact n-1 tuples. N-1 moduli. If n is 2, then there is just 1. There is a Kloosterman sum, SW, which depends on, this should be p to the m, not m, but I can't reach that anymore.
You say a word about this engineering. I mean, you can talk about all aspects, but one thing that you're immediately writing this is coming from this formula. There's an issue of engineering. Kuznetsov's contribution was to make an invert the transform, and that was on the other side. So usually you make Poincare series or something, and then you have a function there, and then you have to engineer.
Right.
Is the aspect of engineering here, I assume, is not an issue.
It's not trivial, but it's not very hard either, because the Archimedean place is fixed. And so I just need a function that is non-negative.
Yeah, so you don't do any inversion, you just put your function in the Poincare series.
Yes. That's one of the reasons why treating an Archimedean family in this sense is much harder, because then you really need to do something at the Archimedean place. Here we don't need to do anything. No serious work is required at the Archimedean place. Okay, so it has some input, which is basically p to the m, but this is irrelevant. Then there are the moduli. I have to divide by all the moduli. And that's basically it. There is some weight function, but that's not interesting. And I need to know how long this sum is. And of course, the larger the Hecke eigenvalue is, the more I get punished in the summation length. And you can check, this is also mediocre, it's not so hard to compute. The sum runs up to p to the m. Okay, let's take this for granted, and I will discuss this now. I want to discuss several things. I will want to give you the definition of this Kloosterman sum, which is really quite interesting in a moment. And let's do some numerology. What do we need? So first of all, in this setup, we cannot beat the trivial element. The trivial Weil element contributes 1. That's something we cannot beat. So what do I want? Okay, so I definitely have, so from the trivial Weil element, I definitely have a contribution volume divided by 2 sigma m. That's something I cannot avoid. And what's the goal? The goal is volume to the power 1 minus 2 over n minus 1 sigma. This tells us how to choose p to the m. So this tells us that we need to choose p to the m to be volume to the power 1 over n minus 1. If I do this, then I just get volume to the power 1 minus 2 over n minus 1 sigma. Yeah, so that's the numerology that I need in order to reach my goal. Maybe even better, but certainly I can't do, I mean, that's definitely what I need. Okay, let's remember this. And now I want to talk about Kloosterman sums. And yeah, because that's okay, maybe this blackboard suffices. So what is this Kloosterman sum? SW it's a sum, and as you can see, it depends on the Brüha decomposition. So what do? I write a group element gamma as follows. It has a unipotent matrix, then it has a diagonal matrix that depends on C. I will say what C star is at the moment. There is a Weil element, and there is another unipotent element. Here I divide by nz. And to make this unique, I don't take all of the unipotent. I'll define what that is in a moment. So it's this double quotient. And I forgot one thing. And of course, it has to be a matrix that's in my subgroup gamma. So I intersect this by gamma. That's what it is. And so accordingly, I write my gamma as a matrix B1, C star, W, B2 in this double quotient. And then I have two characters, one here and one here. And these characters depend on the star. And I owe you a definition of NW. NW is W inverse NW intersected with N. N is this. And C star is 1 over C n minus 1. It's a diagonal matrix. Cn minus 1 over Cn minus 2, and so on, C2 over C1. Yeah, so an upper triangular matrix, a diagonal matrix, a Weyl element, and an upper triangular matrix. This is the Kloosterman sum. Okay, you may not recognize this as a Kloosterman sum. So in order to get used to this, let's do a little exercise. Let's take the case n equals 2 and recover from this definition the usual Kloosterman sum. Okay, and let's take as a Weyl element this Weyl element. Okay, how does this work? Okay, so we take a matrix B1. That's B1. Then we take C, which is 1 over C, C, diagonal matrix with these entries. Then we take the Weyl element, and we take B2, which is 1y1. And now it depends on how good you are in matrix multiplication. So you have to multiply these four matrices. I prepared this because I can't do this on the blackboard, but I asked Mathematica to do it. And that's the result. And this matrix has to be in SL2Z, has to be integral. But remember, X and Y are rational numbers. X and Y are rational, but the whole matrix has to be integral. So what do we learn from this? First of all, C must be integral. Only integral moduli are allowed. C is integral. Next, X can have at most denominator C and Y can have at most denominator C. So X and Y are in 1 over CZ, but of course modulo Z. So they run through a residue system modulo C. And then we have this, and actually I did a mistake because there is a minus sign. Here's a minus sign. And now if X and Y run through a residue system modulo C, you see the congruence XY is congruent to 1 mod C. Yeah? And you recover the usual Kloosterman set. So this is sum XY is congruent to 1 mod C. And then you have the two characters. And this is exactly what you expect for an ordinary Kloosterman sum. Yeah. So for the case n equals 2, long Weyl element, this congruence gives you the usual Kloosterman sum. But you can imagine that in higher rank, this procedure becomes not so nice. Yes.
In the dimension of n sub W, that W inverse n transpose.
Oh yeah. Now here's the transpose. Okay, and I want to study these Kloosterman sums, and there are a couple of questions you can ask. So obviously these Kloosterman sums are relevant because they come up here, and you want to understand how they behave. And the first question that I would like to ask is, what is the trivial bound? And by trivial bound, I mean I forget the characters and just want to count the number of double cosets. So let's say XW is the number of double cosets. How many double cosets are there? Second question, what about non-trivial bounds, where you exploit cancellation from the character? And third question, very important for application, when is this zero? So what are the conditions on the moduli C so that it actually vanishes? When does this vanish? All right. So number one, the trivial bound is actually a theorem, but it's a hard theorem. It's not easy. It's a hard theorem of Dabrowski and Reeder from 1997. And they prove that XW.
What group are you doing now?
What's that?
What gamma?
For the moment, gamma can be anything.
When they're dealing with it, yeah,
What's that?
what are they dealing with?
They are dealing with the full group, so SLNZ. Of course, any bound for SLNZ is also a bound for a congruent subgroup. That's clear because you're only counting fewer double cosets. So somehow the trivial bound is the product of the moduli, maybe with an epsilon. And this is sharp for the group SLNZ. And we'll see to what extent this is sharp for other groups. But again, this is not easy. So next, non-trivial bounds. This now very much depends on the Weil element, and the classical result is, among others, due to Friedberg, but well, basically Friedberg observed that for a certain Weil element, these are Deligne hyper-Kloosterman sums. And so if W is this Coxeter element, then this Kloosterman sum is a Deligne hyper-Kloosterman sum, and you have non-trivial bounds. In fact, the best bounds you can expect. For other Weil elements, this was unknown for a very long time. And I think the first non-trivial bounds are from last year. And this is a paper of myself with a student of mine, Man, and independently also by Miao. And we can treat the long Weil element and another Weil element that will later play a role. Which is this. So for these two Weil elements, we have non-trivial bounds in general. So XW is bounded by C1 up to Cn minus 1 to the power 1 minus delta. And
It's not, what are you using?
To prove this,
Yep.
let me say.
In other words, it's not square root, right?
No, let me talk about this. This is very interesting. So first of all, how do we prove this? So maybe just one sentence.
Just a question.
Yes.
N equals 3. So N equals 2, there's nothing. N equals 3, there are these, the one that Friedberg you mentioned. There's the other one's a product of two GL2 clusters.
Yes.
Right. Okay.
Yes. Let me come to this. Okay. So because you mentioned this formula of Friedberg and Goldfeld and others, this uses Plücker coordinates. And unfortunately, this is pretty useless in higher rank because you don't understand the Plücker relations. So this is not going to work. What we do is the second thing that you say. In general, these are not products of GL2 Kloosterman sums, but they are nested GL2 Kloosterman sums. This is not easy to see, but you can write, this is not a triviality, but you can write this as nested GL2 Kloosterman sums. And then you can basically apply Weyls bound for one of them, and this suffices. This, for those of you who know what I'm talking about, this reminds me a little bit of State's formula. You can write the GLN Whittaker function as nested integrals of Bessel functions. And this is a bit similar. You can write the GLN Kloosterman sum as nested sums of GL2 Kloosterman sums. Yeah. So next discussion point is, what about delta? So the delta that we get is O of 1 over n squared. So it's not tiny, but it's not very big either. Perhaps one can show 1 over n, but not better than that. So square root cancellation is definitely wrong, at least in general. We also have lower bounds, and we have lower bounds of that order of magnitude. So this is the limit. In general, square root cancellation is violated for these higher rank Kloosterman sums. Okay. This may be enough on this topic. Okay, and third point, when does this vanish? And there are several situations. First of all, it's an observation of Friedberg that the Wien element has to have a certain shape. It has to be a block of identity matrices somehow in reversed order. Yeah, so it has to look something like this, where each I is an identity matrix. If it's not of that form, then the Kloosterman sum vanishes somehow for trivial reasons. Secondly, and this is very important for estimations, we'll see an example later, there are consistency relations among the moduli. These moduli C1 up to Cn minus 1 are not independent, at least not in general. For the long Weyl element, they are independent, but in general, they have some relations. And we have n minus the number of blocks relations. Yeah? So in particular, if you have the identity, then there is only one block. So if D1 equals n, we have the identity matrix, the trivial Weyl element, then the number of blocks is 1. You have n minus 1 relations. So you have, all of them have to be 1. Yeah, this is and if you have the long Weyl element, then you have n blocks and you have no relations. And the relations are of this form: Ci minus 1 times Ci plus 1 equals Ci squared. And such a relation is very powerful, because if you know Ci by its divisor argument, you also know these two. Yeah. So such a relation, if it exists, has severe constraints on the moduli. And the third condition are divisibility properties. Divisibility properties. And this is something we are very, very familiar with. If we apply for level Q, then like all of the moduli have to be divisible by Q. And things are a little more complicated in general. You can recover CK, the kth modulus, as a minor of the matrix gamma that you're looking at. So if this is your gamma, then you can recover C from this by taking a minor of the k bottom rows and then some columns. And so you see, I mean, because even in level Q, like even for gamma naught of Q, the bottom row is divisible by Q. This is congruent 0 mod Q. So all the moduli are congruent to 0 mod Q, but you may have more.
First is a condition for non-vanishing, and the second two are conditions for vanishing.
Yes. Okay. Yes, if I write this. Okay, fair enough. Yeah. Okay. So for non-vanishing. Yeah. Well, this is also a condition for non. I mean, this has to be congruent to 0 mod Q, and then it's non-vanishing. Okay. So let me return to our trace formula here, and let's apply what we have in various cases. Okay, case 1. I take as my congruence group gamma naught of Q. Okay, we need to deal with two things. One is the question whether I can just throw in an extra Fourier coefficient. The other one is what do I do with these Kloosterman fields. So Fourier coefficients is very simple because we have newform theory and then and there's an important point. So this f of 1 is essentially an L value at 1, but in the denominator. This is important. So in order to sneak this in, I need upper bounds for the L value at 1. And that's something we have available in great generality. If I needed lower bounds, I would be in trouble because then I run into Siegel zeros.
But you're not assuming Ramanujan, of course. That's the whole point. So you're using the Ivanich
yes.
Homogeneity trick.
Yes.
Yes, it was carried out by somebody.
By Lee, a student of Ramanujan.
Okay.
Yeah. So there is a general principle that was invented by Ivanich to get upper bounds. So I only need upper bounds for L1 adjoint. And that's available in great generality. So this is not an issue. So next, Kloosterman sums. Okay, so what's the volume? The volume is Q to the n minus 1. To the power 1 over n minus 1 means that this sum runs effectively up to Q. But all the moduli are divisible by Q. So if I just arrange the constants appropriately, all of this vanishes. Yeah? End of story. That was it. By divisibility, every W which is not the trivial Wien element vanishes. Okay, that's it, period. So we have a density theorem. So this is too simple. I mean, this is a
that's what's supposed to happen.
Yeah.
Now the density is supposed to be a sort of.
But you'll see later that it can be much more involved. But for in this case, it's really soft. And this is a legitimate proof. But now you can ask, okay, maybe this was too simple. So maybe let's go beyond density.
Where I like to say is you haven't hit the off diagonal, so to speak.
Yes. Yeah. The off diagonals don't even show up. Okay, but let's go beyond density. If I want to go beyond density, then I choose P to the M larger, and then I do see the off diagonal terms. And let's suppose I don't go to Q, but I go to Q squared. So I want something that's twice as good. So choose P to the M to be Q squared, or a little less than that. Then all the moduli Cj have to be divisible by Q. And that's it, because it's just a little less than Q squared. So it's something like this, and Q is a prime. Yeah, so it must be of that form. And so by multiplicativity of Kloosterman sums, what I need to understand is the Kloosterman sum associated with the moduli Q. Yeah? I can split this by the Chinese remainder theorem, and that's what I need to understand. And here something very interesting happens, which shows that Kloosterman sums behave a little differently in higher rank than you might expect.
It's critical here, it's prime, or-
Yes, yes, here it's critical that Q is prime.
Really?
Yes.
Really stuck if it's not prime.
Well, the argument breaks down.
Yeah.
That the theorem wouldn't probably not break down, but the argument breaks down. So the lemma for P prime, n greater than 3, I can evaluate this on the nose. And it equals 0 if W is not this Weil element. And if it is, then it equals P to the n minus 2. And we have we have n minus 1 terms here. So you see interesting features. Number one, square root cancellation is highly violated. There is no way you can expect basis bounty, it's simply wrong. So no square root cancellation. And you can actually compute this on the nose, which is also not expected. I mean, if you think of a Kloosterman sum mod P in GL2, cannot compute what it is. But here you can. It's this. Okay, what do we learn from this? The first nice feature is that the only Weil element that we hit is this Weil element, other than the identity. So from the n factorial, or a little less, 2 to the n Weil elements that could possibly come up, there is only the identity and that. And for this, we can explicitly compute what this part of the Kloosterman sum is. Our saving is very minor relative to the trivial bound, but we have a Weil element with a whole lot of consistency relations. There are so many consistency relations that this sum is actually very small, and the numerology just fits that this bound together with these consistency relations just fits so that you get in this range a density theorem that's twice as strong as what the usual density is.
So wait, so to be clear, you're obtaining a density theorem which is probably as good as Ivanech's in
Yes,
GL2,
yes, yes.
without any algebraic geometry.
Correct.
Yeah, that is surprising.
Correct.
It must fail when n is 2. I'm sorry. Bigger than 3, actually.
Yes, for a good reason, because if n equals 3, then this is the long Weil element. Yeah, I need actually n bigger than 3.
But have you ever, you know that you of course have a, from the unitary dual, you already have non-trivial bounds. With
Yes.
no arithmetic,
Yes,
just purely local bounds.
yes.
Is there some explanation of that through this maybe? That you know?
I don't think so. At least I don't see how this comes. And so let me say, so the proof is really computation by hand. There is no algebraic geometry involved, it's a matrix computation. You can write down, you use the definition. You use the definition and make a computation and you just compute it on the nose. Okay, so this is the case 1 for this congruence subgroup.
And let me just be clear, you're not using any product, no use of A or any non-trivial bound is not used at all.
No, at all.
Okay.
It turns out in the end that for n bigger than 3, but you really need n bigger than 3, the congruences that you get are completely decoupled. And it's just counting with your fingers. But this is an artifact, and you were asking me, do I need that piece prime? Yes, I do. This is an artifact of this particular situation. This is not something that holds in general. Okay, any questions? Okay, just to get a different experience, let's take a different congruent subgroup. Let's take.
So this will give you a bound, because it's an Ivanich type bound, it will
Yes.
give you an actual bound, a non-trivial bound towards Ramanujan, not just a density bound.
Yeah,
How far does it go? Is it not the unitary dual? That's exactly what my question.
so it is, yeah. So it gives you 1 minus 4 over n minus 1 sigma. And if n equals 3,
Then it is exactly right.
at n equals 3, it hits the unitary.
That's what I expected.
Yeah.
But n equals 4.
And then it's worse.
Okay, got it.
Yeah, of course, I was dreaming that in n equals 3, I would get something non-trivial. I don't.
Okay.
Okay. So let's take a different congruent subgroup, the other extreme. This is the smallest congruent subgroup that you can think of, and let's see what happens. Okay, let's start with Fourier coefficients. Okay. And okay, so what is gamma of Q? Gamma of Q are matrices that are congruent to 1, 0, 0 mod Q. In particular, I have a condition on the first off-diagonal term. And to stay sane and not make any errors with normalization, basically this means in the Fourier expansion, it doesn't start with the first term, but it starts with the 1 over Q term. Yeah, so this is not very nice to deal with. And in order to stay with the normalization that we have, let's conjugate the group. And let me look at the conjugate group, which I conjugate by this matrix. And then I get something that has negative powers of Q above the diagonal and very large powers of Q below the diagonal. But this is somehow, yeah, this is much more in spirit of what we looked at before. Okay, but I have a big disadvantage here because there is no newform theory. So just having bounds for L1 adjoint is by far not enough to understand the first Fourier coefficient. So what we actually need is, I mean, we have now a big vector space, it's not multiplicity 1, and we need, and the first Fourier coefficient could vanish, yeah? So I need to show that the first Fourier coefficient is on average not too small. Okay, so locally we need to compute something of this shape. The role of the first Fourier coefficient is can be written as a unipotent integral, some character. This gives me the first Fourier coefficient, and then some matrix coefficient. And I need to average this over orthonormal basis of my local representation with gamma Q fixed vectors. This is the same. Fixed vectors. This integral may not be converged. There is a renormalization process, but let's not worry about this too much. And this now depends on the classification of p-adic representation. Depends on classification of p-adic representations. And the whole point which saves our life is that for p a prime, the supercuspidal representations, which are the building blocks, they simply come from representations of GL Z mod PZ. So supercuspidal depth 0 representations can be parametrized. They come from representations of GLN over a finite field. Z mod PZ. And this is fairly well understood, and you can actually compute this explicitly if you work hard enough. And the rest is an induction process. So from supercuspidal, you go to Steinberg, and then you get to go to parabolically induced. And this is an induction process. Once you understand the supercuspidals, you can do the rest by an induction process. Yeah? And the supercuspidals, they can be understood because we have an explicit parametrization. But this uses crucially that the level is prime or square free. Yeah, square free is just as good, but we cannot do higher powers in this way.
So what do you need to know about this? When you say need to compute it, what do you need about it?
I need to have an upper bound for this and a lower bound for the dimension. I mean, I need to show that this is roughly as big as the dimension.
So you want a lower bound of the whole.
For this, I want an upper bound, and for the dimension, I want a lower bound.
You need the fancy recent stuff, or does Roger House stuff already work yet? You know?
This is fairly classical. If you would go to higher powers, then you would need something else. Maybe what is implicitly in your paper with Paul. This could be useful. But this is fairly classical and suffices in this particular case. Okay. Can I write here? Is this allowed?
Yeah, but you might. That's where you end. You've got to plan it. That's your last board.
Ah, okay. Well, let's take this. Okay, let me briefly talk about Fourier Kloosterman sums. That's the other input. And here it turns out, again by divisibility conditions, only my favorite Wien element, W star, survives. Everything else is being killed. And for this, we can again compute the Kloosterman sum by hand, simply by counting congruences. This is relatively involved. I mean, there are n squared congruences, and you have to count solutions to a set of n squared congruences, but this can be done by hand. Okay, when we had this available, I thought, okay, I mean, we have the two extreme cases, the smallest congruence subgroup and the biggest congruence subgroup, and anything in between by the Fragment-Lindelöf principle should be a convex combination. And this is totally not true.
Hang on, this is the gamma Q case.
That's the gamma Q case.
And can you just be clear what you're inputting score? So on the Kloosterman sum, you are just giving for a trivial bound, I think.
So the input, this is only about the trivial bound. So I estimate the Kloosterman sum by the cardinality of the Kloosterman set.
Yeah.
It's only the trivial bound. There is no algebraic geometry. It's a computation by hand, but it does use classification of representations.
And
but it does not go beyond density. It's just density.
yeah, but it's always going to be, if you ever improve density for the principal congruence group, you can use symmetry, the representation theory, to beef it up. You know that, right?
Yeah.
That's how we prove the gap.
Yes.
The smallest irreducible representation of these groups is very big. So if something occurs, it has to occur with high multiplicity.
That's right.
So it's quite natural that you're going to struggle to improve this. You don't have an improvement of this.
We do. We do have a tiny improvement. So we can do density with 2 over n minus 1 plus a small delta. This delta is tiny, but it uses, among other things, the non-trivial bounds for Kloosterman sums that I talked about earlier.
Okay. All right.
Okay, the remaining few minutes, let me talk about an intermediate case, which shows that in general, there can be many more difficulties.
sorry. If you took gamma q, gamma naught q,
Yeah.
is your favorite. You double without using any non-trivial stuff. What
In the prime case.
and if you're willing to put in, you don't know how to improve that
No,
using cancellation or in close.
no, but this is hopeless. I mean, at this point you cannot use. Then you would be able to prove Ramanujan if you can exploit cancellation in Kloosterman sums.
No, you're still stuck just at the density with twice the.
That's right.
I'm just asking what the best you get. Maybe in the end you'll draw.
I can draw a picture right now. I mean, here is n-1/2. This is the standard density theorem. What we get is n-1/4. And then, of course, you have the local bounds, and they are essentially 1/2.
So which groups?
This is for gamma naught of q.
Okay, that's the one you have the best results, probably.
Yes. And I don't think that the Kuznetsov formula can ever be better than twice as good as the standard bound. I doubt that there is any situation where you can go beyond this. And even in GL2, I don't see how you.
GL2. Many people have tried.
Yeah, yeah.
But say that GL2, you only get to that point after you've used Vega.
Yes, of course.
And then of course, it's going to be hard to go further while you are advertising that you're not using anything.
No,
that's why.
That is true. But I mean, there is no cancellation.
Yes, right. I understand.
So the situation in higher rank is distinctly different. There are different features that are not
This maybe matches then with something. Okay, if it's that explicit. By the way, and for sure that comes with coefficient 1, not some module, like in a half integral weight, you get exactly this feature.
Yes.
But then the actual value is its cosine of the root. And then of course it's about the roots. You don't have a coefficient in front of p at -1.
No. This is equal to. It's an honest equality. I'm always very sloppy with equality sign, but this is an equality. I mean, it's equal. There's no implied constant or anything else. Okay, let me very briefly, and then I stop. Look at the Borel subgroup. Gamma b of q, which is matrices that are congruent to something like this mod q. So this is kind of in between. And so far, we have always won, because in the end, it was just 1 or 0 Weil elements that survived. And here, this is not the case. I mean, in the gamma of q case, the reason was that by this conjugation trick, we got so high q powers below the diagonal that we got huge divisibility properties. We don't have this here. Nevertheless, the volume is again quadratic in q. Yeah, so we cannot hope for this. So a problem, many Weil elements contribute, essentially all of them. And now it becomes a pain to compute these Kloosterman sums. I mean, for one given case, I can do it. I mean, if you give me a Weil element, I can perhaps compute the Kloosterman sum. But if you give me n factorial Weil elements, then I don't really know what to do. And so this doesn't work, and individual bounds don't work either, but we don't need individual bounds, we just need an average. We need an average of Kloosterman sums. So basically we need to know what's the abscissa of convergence of the Kloosterman zeta function. So I need abscissa of convergence of the Kloosterman zeta function. In fact, we are only interested in trivial bounds. So we need something like this, xw of c1 up to cn-1, raised to the c1 to the s1 up to cn-1 to the sn-1. So this is an analytic function in S1 up to Sn minus 1, at least in some half plane. And we need to know what's the abscissa of convergence. So for instance, if n is 2, then this is Euler function phi of c divided by c to the s, and we have an explicit expression. In higher rank for different Weil elements, we can't play this game so easily. In the end, it turns out to be a complicated induction process because all these Weil elements are understood in terms of the bubble sort algorithm. I mean, a Weil element is a permutation, and the way you understand the permutation is by flipping consecutive entries. And so basically you need the bubble sort algorithm to understand this W. And this is a nice algorithmic feature, but it's not so useful in practice, but still you can use this inductively. And basically, okay, there is, I don't have time to explain this, but there is a representation theoretic way you can view this in terms of intertwining operators, and then you have a certain vector space, and in this vector space, you have the Castleman basis, and you need to know how certain operators act on this. And this is a long computation that's done inductively in the end. And in this way, you get the abscissa of convergence, and this is just enough to prove what is needed. But you need to take into account, and that's the hard part, and this is what is not be seen by representation theory, you need to take into account the consistency relations. And for the long Weil element, this is straightforward because there are no consistency relations. But if you have another Weil element, a different one, then you need to take into account that there are relations between the C's. And this means you basically have to design these S's very carefully. And okay, but anyway, so what I want to say is that in some sense, gamma naught of Q and gamma of Q are not representative. In general, things can be more complicated. And this proof uses also some special structure. It does not work for a general group. It uses the Ibaruri structure. So this is the Ibaruri subgroup. And it uses very crucially the fact that this has some special structure. So I don't know what the process looks like for arbitrary subgroups. Right now, we just have a couple of examples, and we are looking at the various features of these. Okay, so let me just summarize in 2 sentences. Applications of the relative trace formula here are density theorems, and we have a general scheme. We need 2 pieces of input, Fourier coefficients and Kloosterman sums. Fourier coefficients depend on some sort of representation theory. Kloosterman sums depend on some sort of combinatorics. And yeah, once you have this available, you can prove something. Okay, thank you very much.
For the other gammas, what are they?
Well, for the other groups, it's just the
You haven't improved the density.
okay, so for gamma of Q,
Say a slight improvement.
yeah, for gamma of Q, we have n-1/2, and here is something like n-2 minus delta. So, and this delta is like 1/n or 1/n squared. So it's a tiny improvement.
And for the Borel?
For the Borel, we just get it on the nose, and we have no idea how to improve this. So it really seems that generically you should get this original density theorem. That's kind of the thing that you want to get.
Yeah.
And everything better requires some particular features. So this can usually not be gotten by soft methods, whereas this has a chance, at least, to be proved by soft methods.
The density, I'd always hoped the density would be soft.
Yeah, but it's, I mean, my feeling is, okay, maybe a clever argument is missing, but my feeling is even that
Yeah, right.
can be very hard. And it's definitely,
Right, and the people who try to use the trace formula have failed. So.
yeah.
Well, I was going to ask about that. So yeah, what would happen if I tried to use the trace or pre-trace formula?
Okay, so as Peter said, I mean, there are papers for Archimedean families, not for level families, but for Archimedean families by Yasmin Matz and her co-authors. And they prove something like this, but this looks like this. So it's basically quadratic in n. So it does give density, but it doesn't match with the trivial representation. And yeah, but okay, I mean, in principle, it's well conceivable that the trace formula could do something for you, but I don't, I mean, okay, I know what the picture looks like in GL2. I showed this yesterday. In GL2, instead of Kloosterman sums, you get L values that you sum up, and if you estimate them trivially, you get density.
You should say class numbers, which are estimated. That's a class number.
It's a class number, yes. Yes.
Yeah, so.
Well, no, it's
No, it is a class number.
it's class number times regulator.
Yeah.
And that's why it's L.
That's what I mean. Yeah, right.
Yeah, but then it's L.
So it's a geometry of numbers quantity that you're trying to get uniform.
Yes.
And of course you can in GL2, I mean, even these very Freitag. Oh, Mikola.
Yeah.
He has quite general, I think he gets density as well, if I remember. But
Yeah, in a horizontal aspect. Yeah, yes.
he's not quite useful, but
Yeah.
the minute you go to higher number fields, then.
Yes.
Kloosterman sums are friendly.
Kloosterman sums are more friendly, although, I mean, at some point you feel they are not so friendly. But yeah, they are in some sense more friendly. Yeah.
And what about other groups?
Which groups? So these are the examples that we have to offer right now.
I meant non-GLM.
Yeah.
Yes.
So I mentioned yesterday that I have a student who looked at the Siegel congruent subgroup of SP4Z. So this is also a study of Kloosterman sums, and here we have a formula of Chen and Ichino for the first Fourier coefficient. You can compare the Peterson norms on SP4 in a that's highly non-trivial. And but then, of course, if you apply Kuznetsov, you only pick up the generic forms. So either you have to reinsert the non-generic ones artificially, or you are happy with a family that only consists of generic forms. But yeah, in principle, you can do this if you understand the machinery well enough. You can do this for other groups.
Interesting when you get an analog with that lemma up there.
Yes. Yeah, I think he looked at this, but yeah, he has quite explicit formulae. So I don't think you get something as clean as that, but in principle here you can also compute the Kloosterman sums relatively explicitly. And again, they are what you would expect them to be. They are nested GL2 Kloosterman sums.
More questions?
Does that strategy also work in a number field case?
Oh yeah, I don't see any reason why not. I mean, this is all local anyway. The Kloosterman sums are local. The representation theory is local. I just, I grew up with Q and
What's interesting is, I think in the end, you're going to have to use some functoriality because what you're using are the unipolar, the parabolic subgroups very heavily to define a Kloosterman sum. And the other ones are not friendly. So like if you want to do a division algebra or something, then presumably the transfer the way Matilda's doing it, coupled with the knowledge on GLM, is the passage to the final solution.
Absolutely. Unipotents are absolutely crucial, otherwise it's not even defined. Yes.
Any more questions? Questions from Zoom? Okay. Seems like none. All right, so let's thank Valentin again for a great talk.